Perché... Perfetto, ci siamo.
Molto bene.
Okay, recording started. I think we can start. Okay. Good. Okay, good afternoon, everybody. Good afternoon also to those who are remotely connected. Time is running very fast, so we already got the last lecture. So today will be our final meeting in physical presence. Of course, we will meet again at the exam. As you know, the exam is in physical presence only. So it's not the last day that we meet, definitely. On the other hand, this closes our interaction in terms of lectures. So take this opportunity today, if you have any question related to what I taught, any question, any criticism, any suggestion for the next year, because it looks like maybe the course will be delivered again also next year. It's not yet confirmed because of some restructuring of the soft skill courses that the university is operating, but it looks like this subject will be kept. So if you have any suggestion, any criticism, take this opportunity. Of course, you can also write emails to me later on, but I'm very pleased also directly from you to get your suggestions. I also would like to suggest to you to stay tuned on the email that I may continue to send to you through Virtuale, because usually when I get also further information, something that I consider interesting related to the topic of climate change and climate actions, usually I like to share this information with the students. And if you're interested, also I will send you an email to remind it, but if you're interested, I am also delivering a course on climate change adaptation at the engineering school, which is conceived in order to be attended also by non-engineering students. It's 6 credits, will be delivered next year in the second semester. I am also teaching it now. So if you're interested for the next year to take it as an elective course, and even if you are a student not attending engineering degree programs, I think it may be interesting, especially, of course, if you're interested in climate change, and I think that you are if you are here. And since you know that some of the students here are also attending this course on climate change adaptation already now, I just want to point out that the lecture that I'm delivering today in the afternoon is similar to an analogous lecture that I delivered at engineering in the other course. It's not the same lecture, but there are many similarities. Okay. Don't forget to mark your attendance today. It's the last day. And I just want to tell you that I removed, as usual, some preliminary crosses that were put there before the start time of the lecture today. Okay. Good. You already have also for the exam the dates, but I will make some comments about the exam at the end of the lecture. Okay, so the last link that we have to click on is design of climate change adaptation actions. And this is a topic that is related to climate change adaptation, of course. So climate actions. climate actions in terms of adaptation. I will specify what adaptation means. And in order to give this specification, I think it's better if I refer to the Wikipedia page. So when we talk about climate action, we may identify two categories of actions: climate change mitigation and climate change adaptation. I think we briefly already discussed the difference between the two. Climate change mitigation means that we take action that aim to reduce, mitigate climate change. So to contrast the changes in climate. And this is typically done by reducing CO2 emissions. These are actions that, for their specific features, need to be taken at the global level. Of course, reduction of CO2 emissions aims to reduce the CO2 concentration in the atmosphere. And it's an action that cannot be taken by just one country. We need a global coordination for this. While when we talk about adaptation, as we will see, adaptation is made by local actions, maybe a combination of local action, a global combination of local action, but the individual contribution to adaptation is always given at the local level. Furthermore, there is an important difference between the two categories in terms of time scales. So climate change mitigation, as you know, produces effects in the long term. Climate has an inertia, which means that if we reduce the CO2 concentration in the atmosphere today, we will see the beneficial effects in maybe a couple of decades. It's not an immediate effect. These timescales are not fully clear. For sure, there are some impacts, some benefits that can be attained also in the short term, like, for instance, a reduction of pollution of the air, a reduction of concentration of certain pollutants and greenhouse gases. But in terms of climate, we still believe that the effects, like on the global temperature, will be visible in the long term. So this, on the one end, is a nice feature because it means also that once obtained, the target will be long-lasting. You understand why? If there is inertia, it means that the time required to get to a new equilibrium situation is long, but it also means that the new equilibrium will be maintained for a long time. So this is good. On the other hand, the fact that the time scale is long it's not good for the solution, for the timely solution of local problems. And therefore, you know, this is indeed a limitation. Climate change adaptation means that we are not attempting to stop climate change, but we are adapting to it. We are upsetting it and adapting to. Which means, like, for instance, if the temperature in a city is dramatically increasing, I give money to people to install air conditioning. This is adaptation, a clear example of adaptation. It doesn't solve the problem at its roots. It gives the means to adapt to the problem. Climate change adaptation is still very important, even if it doesn't solve the causes of the problem. It's still very important because in the short term, immediately, allows to mitigate the impact of climate change. It doesn't mitigate climate change, but mitigates the impact of climate change, which is extremely important because going back to the case of air conditioning, if you have an hot wave, people may die. People may get sick. If you adapt, you avoid the death or the sickness of people. So it is indeed important, produces immediate effects. It is also good because it's a local action, which means that we may have a more direct role in the activation of these actions. So the individual contribution, given that it's a contribution at the local level, is easier to make with respect to a global strategy, which means that even local administration with which it's easier to interact may undertake important actions. So this is another good feature. On the other hand, the bad feature of adaptation is that it doesn't solve the problem and may be a temporary solution, because if climate change continues, and so if temperature still increases, we need further adaptation. From this definition, you understand that the ideal solution is the combination of the two things. The climate change adaptation for solving the immediate problems in a short time frame, and climate change mitigation to resolve the causes of the problem. On the other hand, we have limited resources to cope with climate change. These are interventions that require a lot of resources, and therefore sometimes we cannot put in practice both of them. We need to make a choice. And therefore, depending on the perspective, the point of view, depending on the impact of climate change, you may get different opinions from people, from politicians, from administrators on the priorities to give to mitigation rather than adaptation. You may get different views. This is normal. This is completely fine. The important thing is that the selection of priorities is done with proper consideration of pros and cons. It's important that we give the correct priorities, which depend on the specific situation at the local level. So this is climate change adaptation. So what is the definition? Is the process of adjusting to current or expected impacts or effects of climate change. Adaptation may imply to avoid harm, but adaptation also implies to exploit opportunities. This is extremely relevant. Climate change doesn't bring only problems, it also brings opportunities. If you look at past climatic changes, past warmings after the glaciations, for instance, you understand what is the benefit, the opportunity that past warmings produced. It is imperative that we try to benefit from these opportunities, because this is a basic concept of resilience. We get resilient. We will see in a moment what resilience means, but we will get resilient with respect to a new configuration of the environment if we are able to mitigate the adverse impacts and take advantage from the opportunities. Let me give you an example. If you think about food production, agriculture, it's clear that with the global warming, you have some cultivations that may be dropped and others that can grow better with an higher temperature. The classical example is the quality of the French wine that is increased after global warming in terms of alcoholic content. So we don't have to hesitate to change our development model in general, not only in agriculture, to basically drop bad practices with respect to an emerging new climate and adopt better practices to take advantage from the opportunities. Adaptation may be incremental, adaptation actions may be incremental or transformative, with pros and cons that we will discuss. Incremental actions present the big advantage of requiring less resources to be started, because you can start with the minimal solution and then increment the action. Present the advantage of being flexible. So in case we make an erroneous design or an imprecise design, incremental actions allow you to make corrections transformative actions are a little bit more risky, but may present more interesting opportunities in the future. So this is always a dilemma when we have to choose between keeping with some updating the status quo or operating a transformation, introducing an innovation. It is a typical dilemma. So typically innovation, transformation, transformative actions require more risk, more resources to be started, but in the long term may present interesting opportunities. Adaptation is particularly important where the conditions are particularly disadvantaged with respect to coping with climate change. So if you have a situation that is already critical, adaptation becomes more important. So low GDP, low gross domestic product countries may require more urgently adaptation because they are more exposed to climate change. By definition, in countries where the gross domestic product, the high income countries, these are more advantaged to cope with climate change because adaptation requires resources, mitigation requires resources. So these countries which have more resources are in a more favorable position with respect to more disadvantaged countries. This is particularly something that we have to take into account. Okay, let me go back to my lecture here. And there is also a similar link in Wikipedia for climate change. Oh, sorry, it's here. For climate change mitigation, but we are not opening it now. For moving forward with my lecture, I move to the PowerPoint, which can be downloaded at the end of the lecture. I just want to tell you that the PowerPoint is a bit shorter with respect to the web page. This is nothing concerning for you. You have to refer to the web page for preparing your exam. I just wanted to alert you. And once again, to prepare the exams, may I suggest you to refer to the web page and not to the PowerPoint, which is just useful for delivering the lecture. It's more efficient. Just 1 second. Okay. 2 examples of in this picture of climate change adaptation: solar panels, wind farms for energy production. Solar panels, you know, pros and cons, and the picture clearly shows the pros and cons of these plants. So solar panels are using part of the land. There is a problem in terms of visual appearance of the land. There is also a problem in the interference they have with the hydrological cycle because solar panels are not permeable. So under solar farms, we have reduced infiltration. We have more production of surface water, which is not very good. It's not good for the state of groundwater systems. It's also not good for in case of flooding, because an increase of surface runoff production means that the land is more exposed to flooding. Maybe this is not relevant in some cases. Wind farms, the problem is again the visual appearance, and the problem is the noise. So first thing to note, any adaptation action has an impact. So this is I don't know how to pronounce it, is a vicious circle. In Italian, I would say circolo vizioso. Means that we have an impact by climate change. We try to reduce the impact by adapting, but the solution for adaptation also have an impact. So, I mean, we have to carefully consider these impacts because in this case, you may think that the impact is really not so bad. Even if I can tell you, if you get an opportunity to get close to a wind turbine, take this opportunity because it's really very noisy. So you realize that if people are living in the vicinity doesn't mean 10 meters, means 1 kilometer. Even at a 1 kilometer distance, you can feel the noise. There are other adaptation actions that have even a greater impact. Think of a dam. A dam is a classical adaptation action. And it is very, very efficient. In fact, we built a lot of dams in the Western world after the Second War, last century, about 8 years ago, precisely to support socioeconomic development. On the other hand, the impact of dams is clear. Keep in mind that also the duration of these solutions is it's not very extended. If we think of a dam, it may last for, usually the expected lifetime is from 50 to 100 years, which is very short. In some cases, a dam may last for a couple of hundreds. It's unlikely that we succeed in making them lasting more than that. So you understand that it's 200 years. It's a very short time frame. It's of course not regarding our life, but a little bit beyond it, not much beyond it. And if we have a visionary perspective, we have to take a much longer perspective, like 500 or even more than that. Of course, in 200 years from now, we will have different technologies. So maybe that we don't need these adaptation measures anymore. On the other hand, it is a matter of perspective. It's a matter of perspective to think at the duration by taking a conservative approach. It's unlikely that in 200 years we will give up with hydroelectricity. It is very unlikely. So when we think of hydroelectricity, we should have a long perspective. If you think about solar farms or wind farms, the duration is even lower than that. Of course, they can be replaced. Replacing a solar farm is much easier than replacing a dam. Replacing a dam may be impossible. Replacing a solar farm is possible, but there are, of course, materials to displace, and the treatment displacement of these materials is still a concerning issue. Think of electric cars displacing the exhausted batteries. It's not. It's still something that is raising concerns on the sustainability of electric cars. If you think of the number of cars that we have, if all the cars were to become electrical, and if you think of the number of batteries that at the global level would have to be displaced, exhausted batteries, you know, it's still a problem. Okay, now let me focus on this figure here. And let me introduce the concept of resilience. And this is our target. It's a buzzword, but it is a buzzword highlighting a very important concept. What is resilience? As you can read here, resilience is the ability to prepare and plan for, absorb, recover from, and more successfully adapt to adverse events. In these cases, we are talking specifically of weather-related disasters. Climate change means weather-related disaster. Climate change may also mean some other disasters, but mainly we refer to weather-related disasters. Climate change may also cause industrial risk because flooding may trigger industrial disaster. Climate change may originate oil spills because flooding may originate oil spills. Climate change may also have some impact, even if fortunately weak, on the occurrence of earthquakes, which are not a weather disaster, but may be indeed triggered by overexploitation of groundwater, for instance, which may be caused in turn by climate change. Anyway, we refer mainly to weather-related disasters. And here you see that this figure clarifies that resilience can be gained through hazard mitigation, which means climate change mitigation, and climate change adaptation. And there is again the definition of mitigation and adaptation. And when we talk about hazards, you see in this figure, they take a general approach. They consider technological industrial hazards, such as oil spills. They consider societal hazards like terrorism. Terrorism may have an implication with climate change, by the way. There is a lot of activity focusing, research activity focusing on international migration and then political tensions caused by climate change. We don't have to attribute to climate change any problem that we experience today, but I'm just trying to highlight what could be the connection, which we cannot neglect. Without, I don't want to be too alarmist, but I just want to raise your awareness and stimulate your thoughts. And then we have the so-called natural hazards. The word natural hazard means hazards related to the natural environment, caused mainly by the natural environment, earthquakes, storms, etc. So the word is very clear. So natural hazard is not including terrorism, is not including an industrial disaster. So the wording is very clear. On the other hand, the use of this term is today questioned because it gives like the feeling that these hazards are not caused by human impact. Actually, all the natural hazards are to some extent influenced by humans. Again, in this case, I don't want to attribute to humans any hazard that we are exposed to. It's clear that they have a natural origin. On the other hand, it's also clear that these hazards may be caused or increased by humans. And therefore, the word natural hazards is considered today a little bit misleading because it looks like non-human induced. So just keep in mind that what we define as natural hazards may have an anthropogenic origin, may be caused by humans. Climate change is a clear example. And if you look at the lower line, you see that the weather-related disaster here, there is a classification, is not really complete because, for instance, we don't see hot waves here, but it gives you an overview of what we mean, which, by the way, you already know. Okay, so resilience, increase of resilience is our target. Climate change adaptation is an effort where engineering plays a key role. In climate change mitigation is not the same thing. Climate change mitigation is mainly a topic for atmospheric scientists, for physicists, for chemical sciences. But adaptation, which is related to impact assessment and design of actions, and these actions may involve the construction of structures. Adaptation is a discipline where engineering again plays a key role. And the example of the dam is relevant. Dam is typically an engineering structure. Now, what is the problem? The problem is that usually the role of engineering is not clearly recognized for reasons that I understand, we understand, because engineering is assumed to be, on the one hand, not very relevant to climate. On the other hand, it is also considered the discipline who contributed to climate change, to the development of climate change. Because engineering is responsible for the Industrial Revolution, is responsible for the design of and the implementation of urban expansion. It's responsible for the production of cars, several tools and inventions that are contributing to a massive release of CO2 emissions. And therefore, today, we tend to assume that the best way to mitigate the impact of climate change is using ecosystem services, natural solutions, which is goodwill. As I said, I'm not criticizing. This is, even if I am an engineer, I'm not criticizing, it's a goodwill. On the other hand, I think it is a mistake if we neglect the key role of engineering. Because as we will see, if you exclude a category of actions like the structural interventions, it is unlikely that we can succeed completely. And second, there are some adaptation actions that are very urgent, which require structural interventions like dams. And neglecting the use of these interventions in all cases, I fully agree that we have to try to limit the solution that have the highest environmental impact. As I said, any solution has an environmental impact. And I think, and I fully agree that we are strictly required to limit this environmental impact, and therefore to limit the solutions that have the highest environmental impact. But on the other hand, where these solutions are necessary, we don't have to hesitate to implement them, because especially for the developing countries, for the more disadvantaged situations, if we neglect the use of these solutions, I think the disparity, the inequality between some countries of the world and other countries will increase. In fact, this debate is very active today in the Eastern world. In the Eastern world, they were late in building dams with respect to the Western world. They started later because the reason is very simple, because of political conflicts. So when did the Western world start building dams and stimulating the socioeconomic development? After the Second World War. The Eastern world started later because their tensions were resolved later. And therefore they are starting now. And if you look at the list of the biggest dams in the world in Wikipedia, you will see that China realized recently several of the largest dams in the world. And this is precisely to support their development, to take advantage from this opportunity, which is indeed unique. So if today the Western world imposed to limit the construction of dams at the global level, after the Western world has profited from all the opportunities, you understand that this would be a policy that would increase the inequality. And therefore, these are issues that have to be considered at the global level. So let's not to forget the role of engineering. Let's not to exclude the interventions that may require, when needed, the realization of further structures. I think I already discussed this. I may just say that a successful adaptation requires an involvement of multiple subjects, multiple institutions, and multiple identities like stakeholders. So a close connection, a close dialogue between administrations, politics, governments, and stakeholders, which means entities that have an interest related to the actions we are studying, and the interest is not only economic interest. Stakeholders are also people living close to a wind farm, even if they don't use the energy that is produced by the wind farm, they are close to them, and therefore they may suffer from the noise. And for this reason, they are stakeholders. So the involvement of multiple stakeholders is a necessary requirement for a successful adaptation. You may think that this is a positive development, and nothing is wrong with it. Actually, there is to say that when you get into a discussion, a lot of entities, the discussion becomes more complicated. One thing is to discuss among 3, 4, 5 people, and another thing is to discuss with 50 people. You have to listen to everybody. And of course, the more the people that get involved in the discussion, and the more the different views, and the more the criticism that you get. And this is particularly complicated when you involve entities which have a different background in terms of education, in terms of skills. They have different perspective, different interests, contrasting interests. So interacting with stakeholders, with several stakeholders, may imply that no final decision is taken. Let me close the door. No final decision is taken, and no action is taken. This happens quite frequently in climate change, where everybody knows the problem and everybody blames the problem, but nobody takes an action. And the reason is that this interaction between different stakeholders is complicated. This is one of the 2 main reasons. And therefore, you understand that in dealing with complex discussions, it becomes also important the way you manage it. So the role of the engineer is essential, but also the role of a social scientist is essential. Managing the discussion is essential, and decision theory may help. The reason why in climate change decision theory is called into play, we don't discuss decision theory here, but you may listen from several people that decision theory is instrumental to taking actions to mitigate the impact of climate change. Why? Not because, decision theory also helps in selecting an objective solution. So in making an objective selection of solution, but the main contribution of decision theory is in the management of a discussion, in the proper involvement and communication with the stakeholders. I mentioned that we have 2 reasons why we don't take actions, or very rarely we see satisfactory actions to mitigate the impact of climate change. The second reason is that actually is the reason why we are here. Because actually, in many cases, we don't know how to do. So when we come to a discussion that has to choose between alternative solutions, we are already at a good stage. We have solutions. But in some cases, we don't really know how to do. So we have a risk of drought that is increasing. How to mitigate the risk of drought? And in particular, how to estimate quantitatively with a number what the risk of drought will be in 50 years from now. We don't know how to do. And this is the reason why when you read reports, even scientific reports on climate change, there is a lot of text dedicated to pointing out the problem. There is a lot of text dedicated to a qualitative prediction of what climate change will be, what the problems will be. There is a lot of text over the overarching strategy, like we have to mitigate CO2 emissions. But when it comes to solution in practice, you find only limited information. And the reason is, as I said, that we still don't know what to do with respect to certain problems, like global agreements for reducing CO2 emissions. Okay, it's relatively easy to bring the head of the states together and sign an agreement, but then who controls that the actions are taken, and who makes sure that the countries have the resources, because will is not enough. We need will and resources. So, I mean, the problem is interesting. I think, okay, let me just say a few things, very general things about decision making. And let me start from this figure. And I am explaining it. The previous two slides explain this figure, but I prefer to introduce the explanation by looking at the figure. So let's look at the left columns, vertical direction columns. Let's look at the so-called top-down approach. This is the usual approach that is taken when studying actions, designing actions against climate change, both mitigation and adaptation. We produce future climate scenarios with a climate model. You know what a climate model is. And then we route the climate scenarios. We give the climate scenario as an input to an impact model, a model that is estimating the impact of climate change in terms of hot waves, cyclones, tropical cyclones, floods, droughts, whatever. We have an impact model that takes the new climate and makes a prediction of what will happen in terms of the identified hazard, flood, droughts, etc. And then this model produces the project variables, the numbers that we need, the quantitative numbers that we need, because it's not enough to design an action to know that water will be less in the future. We need to know how much less water we will have. And then through these project variables or design variables is probably a not very good translation from the Italian variabili di progetto. Design variables means project variables, means the numbers that you use to size an action, to quantitatively define an action. Do I need a dam? What is the capacity? This is the number that I need. And then we get to the strategies, to the identification of strategies. That is a very logical approach from future climate to future impact to future design or project variables and future strategies. It's very, very logic. But what is the problem here? The problem is that climate scenarios have uncertainty, transformation models have uncertainty, and therefore your project variables are affected by inflated uncertainty, because you route uncertainties through uncertainties. In the presence of uncertainty, you already know that we are required to be conservative. So what is the result? The result is that the climatologist, when elaborates a climate scenarios, tends to be conservative, which means that probably we take a future climate that is worse with respect to the truth, which is fine. The impact model, there is uncertainty, and we tend to be conservative. What is the moral of the story? The moral of the story is that we oversize the actions. These numbers, capacity of the dam, are overestimated. So more resources are required, which are not efficiently used because we have a measure that is overprotecting us with then a higher environmental impact, and more resources to be found. And the final result is that very often we have no resources, nothing is done. So this is a third reason why very often we don't take actions. So we realize that, the scientific literature, the scientists realized that, and therefore they proposed a different approach that is maybe less logic, but it's more technical, more efficient, more to the point. So this approach is called bottom-up. So it starts from considering the current problems. It starts from considering, instead of the problems, solutions directly, what is doable. So what is the size of a dam that I can reasonably build, depending on the resources that I have, depending on the environmental impact that I'm willing to tolerate. So let's start from the solution, or let's start with the problem. Did I get a flood? Okay, fine. Let's start from the problem, vulnerability to floods, and let's solve it. And then these strategies, these problems are used to define actions, and then the actions are verified with the climate scenarios. So to what extent the solution that I found is resilient against the climate that is predicted to occur in 2050? And then the answer may be not much resilient. Maybe it is resilient. Okay, that's fine. Problem is solved. Or it's not enough resilient. If it's not enough resilient, is it possible to update this action in the future? Or is it possible, in view of the resources that I have now, to update now the solution in order to make it more resilient? And this reasoning may help you to identify solutions that can be updated, solutions that have more flexibility. And therefore, I mean, you start from an information, possible solutions, current problems, which is not uncertain. Current problems correspond to something that we are experiencing. Of course, there is uncertainty, but it is very much reduced. Of course, when we identify the causes of a disaster, we still have some uncertainty, but it's much less the uncertainty related to assessing something that occurred with respect to assessing something that is predicted. Therefore, we start with less uncertainty, and the uncertain part of it, the climate scenario, is used as a verification, not as a starting point. So this is something that is looks more coherent with the attempt to identify no regret solutions, another buzzword. No regret solutions. So if you focus on the current problem and you solve the current problem, the solution is a no regret one. And then maybe that the solution doesn't last for a long time if climate continues to change. But then we can already now plan some updates for the solution, some flexibility. We can design the solution to ensure some flexibility. Or we may unfortunately conclude that there is no way, if we want to resolve the current problems, we have to be aware that the solution is just a temporary one, but it is anyway much better a solution than taking the risk of doing nothing like we are doing now in many cases. I mean, every year in Italy, we have a lot of tragedies, of disaster caused supposedly by climate change, or in part caused by climate change, or related anyway to climate change. So this calls for a urgent solution, but we have limited resources, and we cannot allow a social cost that is too high for these solutions. So we need to be effective in implementing the solutions, but on the other hand, we don't have much resources. So the bottom-up approach is the only possibility. Now, let's look at the central column and the right column. You see differences, different approaches. It's not different, the concept. The concept is to start from the assessing what we can do now and what are the problems now. But the workflow is a bit different. So let me describe it a little bit. The central column, RDM, stands for robust decision making. Robust decision making aims to seek a robust solution. Robust means, I think we already clarified this, means something that is not ideal, is not perfect, but it's not perfectly wrong. And in fact, a no regret solution is precisely what we aim to. It's not an ideal solution, because the ideal solution is a long-lasting solution which is effective up to 200 years from now. But it's not an ideal solution, but it's a solution that resolves the current problem, and therefore is not completely wrong. It's not perfectly wrong, for sure. So robust decision making starts from the strategies, so starts from the solutions directly, and evaluates this solution against the climate scenarios, and then identifies the vulnerability with respect to the future of the current solutions, and then, if needed, may elaborate and test new strategies to increase the vulnerability in the future. And then these new strategies have to be evaluated again against the scenarios. The right column presents an approach which is called decision scaling. Decision scaling focuses on vulnerability and then uses the scenarios to assess future vulnerability. So not future action, future strategies, but future vulnerabilities. And then allows to use further information to estimate future vulnerabilities, like, for instance, personal perception of the modeler, or historical information, something that is not directly related to climate scenarios, and then it comes out with the strategies. So you may wonder why two different approaches, why these different workflows. It depends on the problem. You may have practical problems to solve, which require you to start from the strategies, because the strategies are already clear. Like, for instance, I want to cope with less water, with not enough water. So there are two possible strategies. I build a dam, so additional storage of water, or I minimize the leakage of water during distribution. And therefore, you get involved in these discussions, strategies are ready, and therefore a workflow like the central one is more appropriate. In some cases, you still don't know the solutions. You have vulnerability, but you have also to discuss the solutions. So it's better to start from the vulnerabilities and assess future vulnerabilities. It's just a difference of workflow, depending on the context. And beware of one fact. When you talk about climate change, the problem, it's difficult to generalize it, to formulate a comprehensive and universal approach. Depending on the climate change, depending on the climate variable that is interesting to you, depending on the local context, you have to take a different approach. It is something that you cannot embed into a software and decide on the PC. It is something that cannot be translated easily into a unique decision support system. You need to contextualize the problem. You need to assess what is available in terms of information, what is available in terms of resources, and then structure your decision, your technical design, if you're involved, in a very specific way. This is why you see here several different alternatives for making the design. The previous two slides basically say what I just said, so we can skip them, okay? Let me just think, yeah, I think it's okay. We already discussed how to obtain future climatic scenarios with climate models, and I just want, so we don't need to spend time on this slide. I just want to emphasize once again that climate models are not the unique way to obtain future climate scenarios. There are also some more traditional approaches which can be used, especially when you have historical data of past climate. And therefore make sure that once that you get involved in some tasks related to climate change, all the available information, all the available methods are considered and possibly used. In any case, we are talking about predictions of the future, and predictions of the future, whatever is the science behind it, are always affected by uncertainty. So just let's keep this in mind. This is very clear to us in every day of our life, but for some reason, sometimes when we talk about weather and climate, we tend to assume that we can make a certain prediction of what will happen. I'm not sure why there is this convincement. I'm mainly working in hydrology. In hydrology, we are well aware that any prediction, even a short-term one, is affected by a relevant uncertainty. And we know that when we make predictions like I'm planning my vacation for next summer, we know that there is uncertainty. Even for our life is full of uncertainty, which is fine. It also makes it more interesting. But on the other hand, let's not to forget it when we talk about climate. We already talked about tipping points. I just want to show you this figure, which is not included in my other lecture, which clarifies one thing. I have to remember for the next year, if I teach again this course, to embed this figure when we describe the tipping points. I think it is a nice figure because it clarifies that before reaching a tipping point, even under change, we can make easily a prediction. The first part of the graph until the vertical white dashed line is quite easily predictable because you see that there is a first part that is not much changing. Second part that starts to change, but on the other hand, the change is very regular. There is an increasing tendency. The prediction is quite easy. Uncertainty is limited. But when you get to a tipping point, a critical threshold, the future may become completely unpredictable, completely. So in this case, you see three possible evolutions. And this is something to consider. So we are not sure. You remember the figure that I already shown you. We are not sure how many tipping points we have to deal with when they are reached. There is, in any prediction that we make, then there might be a lot of uncertainty. And it's not a big problem, provided we consider it, provided we are aware of it. It's not a big problem because, as I said, we are used to deal with uncertainty. And the pandemic clearly has shown to us how much the future may be uncertain, but it has also clarified that we can deal with it. Also, the war in Ukraine has clarified that there is also a socio-economic, socio-political uncertainty, but it has also clarified that we are managing to deal with it. And of course, this is a story that is not finished, like the pandemic is not yet finished. On the other hand, it is, I think that it also shows when we deal with these events that we have the means to deal with uncertainty. Okay, now let's introduce a criteria that we can use for design. I want to be very simple here because we don't have to go into the technical details, but I want to give you the concept. So, in the presence of climate change and when designing actions that aim to mitigate a risk, I didn't define what is a risk, but I think you can understand the meaning. Mitigate a risk, mitigate an hazard. We need to identify a number. We need to quantify this risk. And therefore, we can call into play the theory of risk estimation for a generic hazard. A possible approach is to use the formula that you see here, which is, unfortunately, it's in the bottom of the slide, but let me see in the web page if there is a more there are several figures, but I don't want to anticipate them. Okay, this is the formula. Let's call the risk, or you can also look at the formula in the figure. Just focus on the formula for now. The risk can be given by the product of three factors, can be defined as the product of three factors. According to this theory, you may also estimate the risk by using other approaches, but let's start from this theory, which is very, I think, very clear. So what originates the risk? It's an event. In our case, it's weather related, but it's an event. So in order to originate a risk, we need to have to be threatened by an event, an hot wave. What is the risk originated by an hot wave? First, let's define the event. It's an hot wave. Without the hot wave, we don't have any risk. The hot wave may occur, may be likely or not likely. So it's clear that the risk must increase for increasing likelihood of the event. This is our first assumption. The risk is originated by an event. If the event is likely, I have an high risk. If the event is not likely, I have a lower risk. So let's use as first factor of this relationship the probability of getting an event. Whatever we define it, probability is a meaning that can be understood by everybody. Let me just say that probability is a number between 0 and 1, where 1 means certainty and the 0 means impossibility. Okay, so probability of a not wave, or let's say probability to be flooded is clearer. Good. Now, if I am exposed or if I am threatened by an hazard with an assigned probability, I may get protected. Precisely the scope of adaptation is to get protected. If I am fully protected, there is no risk, even if the event occurs. So there is a flood. I am living at the 4th floor. It's impossible that water reaches me. So there is no risk, at least for my physical integrity. So vulnerability can be defined as a number between 0 and 1. 0 means that I am not vulnerable, I am fully protected. 1 means that I am fully exposed. So it's like an index. Other examples of interventions to reduce vulnerability: levees along rivers, classical, or a dam to store flood water, to retain flood water. Okay. Now, what is the third factor? It's called exposure. What is exposure? It is the economic value of the goods that are threatened by the risk. So if there are no goods exposed to the risk, so if I have a flood, the vulnerability is 1, and the land gets flooded, but there are no people, no houses, nothing, just natural environment which is used to be flooded once in a while. There is no risk because there is no exposure. Exposure can be quantified in different ways. We may choose an economic criteria, like economic value, as I said, of the goods exposed to the hazard. You may say that if the risk is to lose lives, the death of people, it's not a good thing to use an economic value to quantify the exposure. Actually, this is what insurances usually do. But on the other hand, you can also choose different units. It's not, we are not compelled to use economic units. Now, given that if I have no probability, I have no risk. If I have no vulnerability, I have no risk. If I have no exposure, I have no risk. It is reasonable to express the risk as a product of these 3 factors. Which means, keep in mind that probability is between 0 and 1, vulnerability is between 0 and 1, exposure is an economic damage. This means that risk is expressed in economic terms because probability and vulnerability are dimensionless. Therefore, if you define an event with its own probability, its own vulnerability and exposure, you can compute risk as this product. Keep in mind that you need an interpretation for this risk. You need to be fully aware of this risk. Risk expressed in this way takes into account the probability of an event. So if you have an event that is really unlikely, close to impossible, but not impossible, you estimate a very low risk. I say again, if you consider an event that is close to impossible, you end up with an associated risk that is very low, which is reasonable. because given that the event is very unlikely, the risk associated to it is very low. Now, today it's very popular to talk about the risk of encountering a bear in the Alps. And what they say is that if we reduce the number of bears, the risks goes down. This is perfectly in line with what we are saying now. If we reduce the number of bears, we reduce the probability of encountering one. And therefore, the risk lowers down. But you don't have to forget that if that event occurs, the potential damage is very high. So keep the two things separate. If I reduce the number of bears, the risk goes down. But if I encounter the only one that remains there, the potential damage is unchanged. So this is to be said because very often we have the laws in force, the regulation, the guidelines that say a dam should be designed with respect to a flood to be able not to collapse with respect to a flood of, and then they say a probability, which is usually very low. But we are not protected against an event that is higher than the design one. So the fact that the risk of collapse of a dam is very low doesn't mean that the dam is 100% safe. It means that the risk is very low, but if you are living just downstream, you may not be willing to accept even the very low risk because it's like a Damocles sword on your head. And you don't want, when it is directly addressed to you, you may not want to accept a reduced risk, which corresponds to an high exposure. Okay, now let's try to give a graphical expression, and this is something exciting, interesting. On the other hand, it requires a bit of reasoning. This graphical visualization was conceived by me, so if you have any criticism, please address it to me, because I wanted to try to explain in a graphical way the concept. And my idea was, in this curve, let's forget about the orange. In this graph, let's forget about the orange curve for now. In this graph, I wanted to first visualize the progress of vulnerability and exposure depending on the intensity of the event. So if we are threatened by an event like an hot wave, the hot wave may be +2 degrees with respect to average, maybe +4, +10, +20. So the hot wave in general, the event may have different intensities, like earthquakes. There is the scale, different intensity. Now, it is reasonable to assume that vulnerability and exposure depends on the intensity of the event. So this is something easy to be understood. So let's try to visualize what could be a possible pattern, a possible development, a possible curve of vulnerability with respect to the intensity of the event. This is just a possibility. What you see with the red line is just one possibility, depending on your case study, depending on your hazard, depending on your problem. You may have other patterns. In this case, what we are assuming, let's look at the red curve. We are assuming that vulnerability is 0, so I am fully protected up to a certain intensity. So let's suppose that I am talking about a hot wave, and I have a cooling system in my house that is protecting me up to a hot wave of +4 degrees. After that limit, the cooling system has not enough power, and I start suffering. Okay, that's fine. So up to 4 degrees, I am fully protected. Vulnerability is 0. And then vulnerability is varying between 0 and 1. And then if the temperature keeps increasing, if the intensity of the event keeps increasing, I get more exposed. And maybe, possibly, I get to a value of vulnerability 1, or maybe not. Maybe that the curve is stopping at 0.6 or 0.7. But still, this is a curve that is not decreasing. Increasing intensity of the event, the red curve shouldn't decrease and possibly reaches 1, starting from 0 and departing from 0 at a certain threshold. Good. Now let's focus on exposure, the value of the goods that are exposed to the hazard. Even in this case, I can assume that the exposure is 0 up to a certain extent, because even if I am not protected by anything, even if I don't have the cooling system, maybe that I don't suffer any damage up to +1 degrees of hot wave. Okay, so let's assume that the blue curve is 0 up to a certain threshold, and then it starts increasing, the blue curve, without a maximum. Exposure doesn't have a max. It's just a curve that cannot be decreasing. And keep in mind that here, I assumed that after a certain intensity of the event, the blue curve is stabilizing. So it's 0 first, and then increasing with a huge slope, and then stabilizes. But it may be different. It may be that for high intensity, the blue curve is steeping up. Maybe. It depends. It depends on the value, on the behaviors of the goods that are exposed. Actually, it may happen that for very high intensities, you have a steeping up of the exposure. It may happen. But let's suppose that, okay, I have this pattern. Good. Now, what happens to risk? This is the more complicated part of this discussion, but I try to make it simple. Risk needs the computation of probability. Probability is not, you may say, it's not visualized here. Actually, I would say that probability is here because I have in the horizontal axis the intensity of the event. And I said that more extreme events are less likely. Less likely means that the probability to see them is lower. Therefore, I may assume that for increasing intensity of the event, its probability goes down, approaching 0. So probability has a different pattern with respect to vulnerability and exposure. Vulnerability and exposure tend to increase, or at least not decrease, for increasing intensity. Probability decreases for increasing intensity. So when I go to the multiplication, I get 2 factors increasing with increasing intensity, 1 factor decreasing. So it may happen, depending on the pattern of probabilities, vulnerability, and exposure, that we reach a max. The max risk is associated to a certain intensity. This is typically what we find with climate change related hazards. There is a max risk in terms of expected max economic damage. With very low probabilities, the risk goes down. This is what I said earlier. So it's clear that identifying that maximum is maybe a very good way of prioritizing actions. So what action do I need for working over vulnerability in the proximity of the maximum? So this may be or decreasing exposure in the proximity of the maximum. This is a first aid to identify solutions, to identify actions. But don't forget what I like to call the impossible event. Because the max of the risk, if you just work on the max of the risk, you don't get protected on the events that are very low probability. So what I call the impossible events. Actually, recently, maybe for the effect of climate change, we are increasingly hit by events which we believed were impossible. And therefore, we don't get protected against them. We didn't get protected against them. So don't forget in this approach, which aims to give priority to the max risk, don't forget the impossible event. Okay. Now, I want to move forward by exploring how different actions, and in particular, how structural actions versus nature-based solutions, also called ecosystem services, also called green solutions. So how we can use these solutions, ecosystem services, green solution, nature-based, versus the structural actions to work on reducing vulnerability and exposure, because this is the purpose of climate change adaptation. Climate change adaptation doesn't work on probability, because probability means contrasting climate change. Making a flood less probable means contrasting climate change, means climate change mitigation. So working on probability is an affair, is a matter for climate change mitigation. Working on vulnerability and exposure is concerning climate change adaptation. So now I want to explore how these two different categories of solutions can be used. Why precisely these two different categories of solutions? Because this is an interesting debate nowadays. Is it possible to adapt to climate change by using ecosystem services, by using green solutions? Is it possible to avoid structural solutions? I anticipate my answer, it depends. It depends. When you have a question about climate change, I have a very famous colleague, a foreign professor, who listed several questions related to climate change, and he brought in sequence the answer, and the answer invariably was, it depends. Generalize, okay? So the answer is, it depends, but in order to understand how it depends, we need to understand how these solutions work, how these solutions get to target. So let's try to explore a little bit more, but let me just anticipate that I will refer to the example of flood hazard, and then to the example of building a dam to contrast flood hazard. And let me also say one more thing before moving forward with the next figure, and maybe before making the break. Now I will substitute in the subsequent graphs, which are still in Italian, so just forgive me, and the translation can be borrowed by this graph here for intensity of the event, exposure, vulnerability. So you have to be a little bit, you have to be patient a little bit with me. But in the next graphs, I want to show the probability on the horizontal axis, because I think it is more meaningful. On the other hand, given that we are talking about technical details, instead of probability, I want to show on the horizontal axis the return period. The return period, I think we defined it. Did we define what is the return period? No? Okay. The return period is the average time between two events which have equal intensity or higher intensity. So I have two floods, two hot waves. For instance, the hot waves, let's give the intensity +2. The return period between the return period of an hot wave with +2 intensity is the average time occurring between two hot waves with +2 or more intensity. So you understand that the return period is related to frequency and therefore related to probability. The lower the probability, the higher the return period. So if the probability approaches to 0, the return period approaches to infinity. And I am then visualizing the return period, for instance, in this curve here. And it is called tempo di ritorno in Italian. So just keep in mind there is a one-to-one association between the intensity of the event and the return period. So the concept behind this figure doesn't change. I mean, I just made a transformation of the variable on the horizontal axis. It's a transformation through an analytical function, one-to-one. So from a conceptual point of view, nothing is changed. Of course, the shape of the curves change because the transformation is not linear. It's not a linear transformation. So the shape, the graphical shape of the curves may change. Just to clarify the mean. And here in this first figure, you see the uncertainty around vulnerability and exposure. There is uncertainty around vulnerability and exposure. There is uncertainty because vulnerability is estimated through an impact model, and exposure is estimated through a socioeconomic model. These models have some uncertainty, less than climate models probably. Let's say probably less, but still they have uncertainty. And in order to move forward with the technical design, we need to quantify this uncertainty. It is not easy at all. It is not easy for climate models. It's not easy for vulnerability and exposure as well. It is a task for specialists usually. And here in this graph, you see that I didn't put the carb risk because I wanted to make it simple. Okay, fine. I suggest that we make the break now. Do you have any question? Okay, perfect. I am.
Can I just ask one question to make sure I understood? Thank you. The difference between vulnerability and exposure, if I'm not mistaken, is that vulnerability is the level of protection from 0 to 1, so from no protection to full protection, while exposure is the potential damage, the potential economic losses. We defined it, right?
Yes, this is perfect. You understood it perfectly. Okay.
Thank you. Bye-bye.
No problem. Okay, let's take the break now. Thank you. Okay, just a couple of minutes. We wait for the students to come back into the room. Okay, so let me close the door. Okay, so let's now discuss on the effectiveness of the two categories of measures that I mentioned earlier: structural measure or hard engineering methods versus ecosystem services, nature-based solutions. And as I said, this effect can be studied, assessed by referring to these curves, vulnerability and exposure curves. And let's focus first on structural measures. And let's try to understand how structural measures may modify vulnerability and exposure. Again, once again, I am referring to an hypothetical case. It is the pattern of vulnerability and exposure may be very different in other cases, and the effect of structural measures as such may be very different. But what I am depicting here is a general behavior that can be identified in several practical cases. Let's focus first on vulnerability, which is once again, the level of protection between 0 and 1, which is ensured by a given structural measure. Usually, structural measures are designed to protect against a design event, an event that is particularly threatening us, like, for instance, the event corresponding to the higher risk. And these structural measures, being optimized for a very specific event, are less effective as the distance from similar events with different intensity increases. As the difference in intensity increases, typically structural measures that are optimized for a specific event decrease their efficiency as the distance from the intensity of the design event and other events increases. The structural measure usually cannot give protection with respect to all the range of events, especially if it's not oversized. So what we find in general is a pattern like the dashed red line that you see here. It's a decrease in vulnerability which reaches a maximum. for an event of a given intensity, and then the difference in vulnerability, the improvement in vulnerability decreases as we get far from this event. In some situation, it may occur that after a given intensity, after a given retro period, the vulnerability is even increased after a structural measure is put in place. And let me give you an example, again referring to a dam. The dam has a storage which is reserved for retaining flood water. And this storage has a limited value. The dam cannot be overtopped. So if the intensity of the flood goes beyond the intensity that can be tolerated by the available storage capacity of the dam, given that the dam cannot be overtopped, what people do as they get close to overtopping is to release water, to open the bottom discharge and release water. And typically, in order to get protected, they release more water than what is received by the dam. So it means that the intensity of the event downstream is magnified if we get close to the limiting, to the upper limit of the efficiency range. In fact, you may have heard in several cases when floods occur that people cast some doubts on the management of upstream dams, because people are well aware that a bad management, or let's say a dam that is close to exceeding its storage may cause a magnification and increase of the flood intensity downstream. And therefore, it's not unplausible what is depicted here. Events with very low probabilities may suffer from an increase of their vulnerability, of the vulnerability of people exposed to them after a certain event intensity, after a certain retro period. Now, what happens to exposure? Our experience suggests that in many cases, the exposure after climate change adaptation increases because people feel more secure, and therefore they invest more money in their socioeconomic development. This is called, for instance, with reference to flood, it's called in the international literature Levy effect. The Levy effect indicates an increase of exposure that follows the construction of a levee, because people feel more protected, more secure. And this often happens with structural measures because they are massive, they are clearly visible, they offer a very good protection. So you see that indeed the decrease in vulnerability that I emphasized here, I depicted here, is indeed significant. On purpose, I did it. I made it very significant because the structural measures usually are designed for a very specific event, but with respect to the design event, they offer a very good protection and therefore stimulate an increase in exposure. So this is what we are expecting with structural measures. And what about non-structural measures? Ecosystem services. Ecosystem services, let me start with exposure because it's simple. They usually don't stimulate an increase in exposure. Ecosystem services are distributed interventions. They are not clearly visible. Each one of them gives a small contribution. Think of green roofs against hot waves. Green roofs, which are in several American cities, they have flat roofs, and they use this adaptation action to contrast the hot waves in cities. They use green roofs, and they are very local interventions. Many of them, a small one, they are effective if you have many. Okay, typically each of them gives a small contribution, but the combination is maybe effective. So, but they are not clearly visible. They don't give a feeling of security. So typically exposure is not increased. This is another good side of ecosystem services. They increase our confidence with the natural environment, our closeness, our vicinity to the natural environment. They make our cities more natural, and on the other hand, they don't encourage a further development of cities. In terms of vulnerability, they are effective. Usually, you need many of them to be very effective. But if you have many of them, you can reach a very good reduction of vulnerability. Typically, the reduction of vulnerability is more effective for events with a low intensity, because if a big event occurs, they are defeated typically. Defeated means that they are not effective anymore. And if you think about hot waves, that's fine. I mean, green roofs can protect, but if the hot wave is really hot, the vegetation on the green roof can be destroyed. And therefore, then the ecosystem service is defeated, is annihilated, is cancelled out. And therefore, typically the range of effectiveness is shifted toward the left with respect to structural interventions. Now, what happens if I combine the two of them? This is what, of course, if we have resources, this is the optimal solutions. Structural intervention, see the dashed line here, dashed the red line, so it's dot line, dashed in terms of dots plus lines. You see that the structural intervention, they are effective, their effectiveness range is shifted toward the right. Nature-based is shifted toward the left, and nature-based is the dotted line. And their combination gives a very good reduction of vulnerability. In terms of exposure, you have the structural intervention, which may stimulate an increase of exposure, but indeed the combination of the two measures probably in general is the best way to follow. Also, it gives more resilience. You combine both of them. Of course, in some cases, you don't have enough resources, and then you have to make a selection with the aid of decision theory. Are you more interested in getting protected with respect to low intensity events? Then nature-based solutions can be your way out. Are you interested in getting protected against the impossible event? It's unlikely that you can use ecosystem services alone. Probably you need a structural intervention that is sized on purpose to protect against the impossible event. In fact, the literature on impossible events suggests when designing structural measures, to check their functioning against the impossible event. This figure also emphasizes that when you estimate the vulnerability curve, you need a hazard-based analysis, which means in this case, the example is the flood, so it's hydraulic analysis. If it is the hazard is hot waves, you need a thermal model of your context, for instance, of a city. So the impact is to be estimated with an hazard-based model. The exposure is to be estimated with a socio-economic model. You don't see uncertainty here. As I said, it is complicated to estimate uncertainty, but it's possible. It's possible, and you can add uncertainty bands to these curves in order to get an exhaustive picture. I think with this discussion on the risk-based adaptation design, we can be happy with what we discussed so far. Everything is on the web, and it's just in Italian for the last 3 figures. And if you give me some time, it's better if you take your exam as soon as possible, for you, not for me. But if you study later on, maybe that I have the time to translate them. Now, let me close this discussion with some examples of adaptation actions, and I think it is better if I go to the PowerPoint here. One thing I forgot to say, I'm sorry, so I go back a little bit to risk-based adaptation design. If we took this approach to design climate change adaptation, we can divide the design itself in 2 phases. And if you look at these curves here, just 1 second, sorry. These curves put probability or return period or intensity of the event on the horizontal axis. The intensity of the event is treated like an independent variable. Actually, the intensity is not an independent variable. It is impacted by climate change. So if we use this approach to make the design, the suggestion is to divide according to the bottom-up philosophy, the design in 2 phases. In the first phase, we consider the climate unchanged. Current situation, we focus on the current problems, current extremes, current probabilities, and current hazards. So if we get flooded, if we get hot waves, and then we study what are the vulnerabilities and the exposures, and how we can mitigate them, reduce them, okay? And then we need a second phase then. We need the second phase of verification against climate scenarios, climate change. This second phase will change the probability, so will change the horizontal axis. The scale of the horizontal axis will change with a one-to-one relationship, with a one-to-one transformation. And therefore, the curves will change. So the result that you are getting here on this figure will change. And then you may see what is the result after the second phase, after climate change, and verify if it's compatible with your standards, with your targets. So the design is divided into phases, and according to the bottom-up philosophy. First, focus on the current climate, identify solution strategies, identify vulnerabilities, and then use the climate scenarios to make a check, to verify the resilience in the future. Okay, so some premises to be considered when designing climate change adaptation. I am more or less reading what is written here. The effect of climate change vary by region, we know that. And vary also depending on the hazard that we consider, of course. The effect of climate change, we already discussed this, may vary across demographic groups. Climate change poses both risks and opportunities. Keep this in mind. There are some decision-making processes which we did not discuss that allows to make a cost-benefit analysis. The effect of climate change must be considered in the context of multiple stressors and factors, which means that you have to consider several contextual variables, socioeconomic setting, etc. We already discussed this. Adaptation comes at a cost. We already discussed this. Adaptive responses vary in effectiveness as demonstrated by current efforts to cope with climate variability. Of course, we discussed this with the CARBs. The systemic nature of climate impacts complicate the development of adaptation policy. Yeah, we discussed this. Maladaptation, we didn't discuss this. And maladaptation may be even worse than no adaptation. So just be careful and beware that there are uncertainties which need to be considered. Of course, if you spend money for solutions that are not effective, then it's a problem because you don't have money anymore to spend to correct the erroneous solutions. And then keep in mind the opportunities given by no regret solutions. So even if climate change doesn't occur, make sure that your proposed solutions, because you have uncertainty in the future. So maybe that in the future global warming reverses, who knows? And we hope that, actually, we really hope that in the future, for some reason, global warming stops. So beware that there is uncertainty, and therefore it makes sense to use no regret solutions. Whatever the uncertainty is, they are anyway solving current problems. Okay, now, adaptation action. Structural and physical adaptation, 3 categories. Structural and physical adaptation in the first category. Physical means includes ecosystem services. Social adaptation, education of people, information, behavioral adaptation. This doesn't require structural interventions. Institutional adaptation, economic, laws and regulation, government policies and programs. So there are a set of solutions that can be used. Engineering is relevant for the first category, is not very relevant in the second and third categories. Other disciplines are more relevant. Typically, as we know, because I repeated this several times, typically it's better to make a combination of solutions, a portfolio, large portfolio of solutions. Okay, one thing, in terms of social adaptation, don't forget insurances. They are increasingly used. So people prefer to get insured, and it's more convenient in some cases to get people insured rather than spending significant resources in adaptation. It's a good solution, not for every hazard, of course, but for instance, for the hazards related to lack of water for irrigation, it can be a solution to get insured, to insure the farmers against lower than average productivity. These are some examples of adaptation actions. Protective and resilient technologies and materials in properties that are prone to flooding, heat-tolerant vegetation, rainwater storage for reducing the water flow in the sewer systems, avoiding urban floods, and keeping water for irrigation. Rainwater storage, for instance, has been promoted in Australia after the long drought they suffered from 2001 to 2010. They are leaders now in rainwater storage. They have a lot of experience, and the result of the experience are also reported in scientific papers and technical papers. Reducing paved areas to deal with rainwater and heat, paved areas in urban settings. Green roofs, we discussed them, requiring more solid foundations for waterfront properties to avoid erosion and to avoid the erosion of foundation. And raising pumps at wastewater treatment plants, yes, in order to avoid urban flooding, you can increase the power of pumps. Surveying local vulnerability, raising public awareness, making climate change specific planning tools like future flood maps. This seems like trivial. Keep in mind that it's not easy because, for instance, in Florence, they had an experience. They published a flood map of the center of the city, because you know Florence is exposed to flooding like it was 50 years ago in 1966. The situation is more or less the same. And they had to withdraw the map after 1 week because people protested, because if you publish a flood map, the properties within the flooded areas suffer from a decrease of their economic value. And therefore, they had to withdraw the map. You know, there are several societal impacts related to climate change adaptation. And I mentioned impacts related to climate change adaptation. There are several societal impacts which make the discussion not easy. Incentivizing the use of lighter colored roofs. Keep in mind that in Italy, when you make changes to buildings like green roofs, you are not always allowed to, because some of the buildings have an historical value. They are protected by the national, I don't know how to translate, the Sovrintendenza for Beni Culturali, which means the national entity who is tasked with the protection of the cultural heritage, the preservation of the cultural heritage. So they don't allow us to put green roofs on the top of historical buildings, which is perfectly fine. On the other hand, keep in mind that every urban setting is different and some solutions cannot be used in Italy. Also, green roofs in the Italian context are not really ideal, because there is a lot of precipitation during winter. So usually horizontal roofs in Italy have to be carefully considered, because they are more vulnerable to infiltration and humidity. And also there is a big temperature difference between winter and summer. So the thermal excursion is very high in the structures. You know, the impermeable layers are how to say, they are the thermal expansion tends to procure a stress to these impermeable layers, and they get fissured, and therefore it's better to have inclined roofs, not horizontal roofs in Italy. But anyway, this is of course a possibility. Buying out owners in flood-prone areas, this is something that we try in Italy. It's a very good solution. There are several flood-prone areas with homes, with houses. On the other hand, we need money to buy out these people. And raising street level to prevent flooding, this is used in coastal areas. Okay, so climate change adaptation is a typical task of engineering, and as such relies on the prediction of future conditions. And just keep in mind that the role of uncertainty and the compelling need then to use all the information that is available. And this compelling role of uncertainty is particularly important to be considered when you talk about the future, of course. As we say, predictions are uncertain, especially the future one. And a comprehensive assessment of uncertainty, unfortunately, is still a task that is in the realm of research activity, in the domain of research activity. I would say that with this lecture, I forgot that I have other 3 slides, and this is, I think I have nothing to say about this, but let me just try, given that this is the last lecture, to summarize the take-home message that I would like it remains in your background. And it's just a few minutes, and then a final discussion about the exam. So, take-home message, I elaborated these few suggestions. The climate system is still largely unknown. Even today, I said, don't assume that we can predict climate with certainty. Deductive means models, and inductive, based on data, approaches can be used to infer the dynamics of the climate system, both of them. And when we can, we have to integrate them. We have to use both of them. Data, observed in proxies. Analysis shows the key role of natural variability and human influence. So let's keep them into account, both of them. They can compensate or they can be synchronous. They can synchronize, meaning that they can sum over each other. But we don't have to neglect neither natural variability nor human impact. Otherwise, we neglect part of the game. The relative contribution of natural and human-induced variability and change is still poorly known. So just keep into account, it depends on the context, it depends. It depends. There is the urgent need of adaptation options, no matter the causes of climate change. So climate change adaptation, climate adaptation is a urgent need. The disasters that are occurring everywhere, every year, clearly speak for that. Adaptation and mitigation need, there is a spelling error, it's singular, should be plural, to be coupled for the sake of building timely and durable resilience and sustainability. Uncertainty assessment is a key information. Sustainability requires the identification of no-regret solutions that may be effectively identified by using the bottom-up approach, namely by giving priority to the solution of the actual critical situations. Climate change assessment, mitigation and adaptation is a rapidly evolving field. This is the very last take-home message for you. It is necessary that you stay updated, as well as it is necessary to invest in science and to technical guidelines and applications. Okay, now a few words about the exam. You have the dates, they are on Alma Esami. Okay, the subscription to the exams is not yet open. I think it is opening on May 2nd, but you should be able to see the dates. The exam will be a quiz, as you know. I will make available on Virtuale later on a test exam. Shorter, the exam will be 30 questions. I will make available a 15-question exam. Later on means when? I'll try to do my best, but you have to give me 1 month's time. By mid of May, the test exam will be ready. I cannot replicate the test exam precisely. I cannot replicate the real exam precisely in a test exam. Why? Because I want the test exam to be anonymous. And therefore, if I make it anonymous, I have to use a different software application over the web. So what you will get is same questions with a different appearance. Okay, and what you will get, it's a feedback. The exam doesn't give you a feedback, not an immediate feedback. I give a feedback after my correction. The test will give you a feedback, but it gives to you, because it's not possible for me to make differently, to make in a different solution. It will give to you only the final score, like you did 3 questions wrong, but it will not tell you what are the questions. On the other hand, you can repeat it as many times as you want. It's anonymous, and therefore, if you get 3 questions wrong, you can make another trial and to see by trial and error what the outcome is. I'm sorry, but if I make it anonymous, I cannot give you the feedback to any single question. Okay. Now, to take the exam, you need to have attended 70% of the lecture. Let me say what they require in principle, okay? We got your attendance day by day by online. Perfect. At the end of the story, when you will know if you can take the exam when you subscribe. So you try to subscribe and the system may tell you, sorry, but you don't have enough, you don't have the right to do that. If this happens and you think there has been a mistake, like you attended all the lectures and the system tells you, sorry, you can't take the exam because you didn't attend the lectures, send me an email, okay? Send me an email. I don't think this will happen. It may happen that you feel like you took 70% of the crosses online, but still the system gives tells you that that's not true. It may happen because maybe that you made a mistake. You thought that 70% was reached and it was not. The limit is not strict. So before writing to me, please wait for checking, wait a second for checking if you can subscribe to the exam before writing to me, because otherwise you understand, if I get 200 emails, I cannot reply to everybody. And at the end of the story, you don't get any reply. I'm supposed to say, sorry, try to subscribe and come back again. So before writing to me, please try to subscribe in any case. And you can write to me now if you are sure that something went wrong, like, sorry, I didn't know that, and I never attended the lecture. So send me an email. I anticipate that in the extreme case that I just mentioned to you, I don't think there is a solution. But in any case, I don't want to leave you alone. So if you really feel that there is an unsurmountable problem, then write me. Otherwise, just try to subscribe first, and you will see that in most of the cases, you will not have any problem, even if you are concerned like, oh, I don't think I got to 70%. Don't be concerned now. Try before. What happens during the exam? First of all, keep in mind that I am forced to make the exam 50 students at a time. So the day of the exam, the day of each exam, I can make only 3 rounds, which means every exam I can make the exam at most 150 students. I don't think this is a problem, but there is a max value of 150 in each exam. So I don't think this will be a problem. It has never been a problem. And the max number I experienced in the past was like 70. So it's half of 150. I don't think, again, it will be a problem, but in any case, just be informed of this limitation. I already mentioned to you what happens at the exam. At the exam, what happens is that you take the quiz, you give me 15 minutes to make the correction. I tell you the mark, and you tell me if you want to accept it, decline, and then try again, or whatever. Okay, and then, of course, if you want, I show you what are your mistakes. If you want, why? Because if I need to make 3 rounds of exams, or if I need to make 70 exams, and every student, even those who got 30 with Laude, ask me to see the results, you understand that we don't finish in the morning. So in your interest, what I suggest is, if you are not happy with the mark, then of course, you have to review the exam. If you're happy with the mark, don't bother about reviewing the exam. It went well, it's fine. You know that the questions were replied correctly. Before the exam, in every exam day, I will explain to you how it works in detail. So there is no need to give anticipate information, like I will explain to you again that you can decline, whatever. I will explain to you how the quiz works. There is no need to know it in advance. It's very easy. The only thing that I say is be careful, because I will tell you again, but I don't know why, but every exam I have some students who prefer their hotspot with respect to using Alma Wi-Fi. So beware, if you use your own hotspot, that's fine to me. On the other hand, if something wrong happens, I'm not responsible for it. If we have a break in Alma Wi-Fi, I said Alma Wi-Fi or Alma Esami first. Okay, Alma Wi-Fi, if we have a break in Alma Wi-Fi, it's for everybody. So we stop the exam and then we start again. But if you have a break in your own connection, resolving the problem may be a bit delicate. In any case, the exam will be in a lab where you can use a wired connection with a PC that will be made available in the lab. Even for this, my suggestion is use the PC that is in the lab. It's a wired connection, it's faster, it's more efficient. If you want to use your own device, that's fine to me. Okay? But on the other hand, final recommendation for the exam, because it may be useful for you for your studies. I have some experience in taking this quiz, and I want to give you an advice. You may be tempted by, like, during the exam, I can use my own device to check on the web what is the correct reply. This is a smart intention, but my experience suggests that you lose time in doing that. It is not recommended. I'm not traveling among the desks to see if you are using something different. I'm not interested in that. If you decide to not to prepare properly and to refer to your notes during the exam, it's your choice. But my suggestion for you is that there is a double advantage in preparing this exam as it should be prepared. The first is that it remains in your background longer, and believe to me, when you get interviews for your job, it pays back. Second, it's faster, and your memory is faster than looking on the web. For the structure of this quiz, 30 questions in 30 minutes, you don't have time to look on the web. So try to get prepared and not to rely on your looking at your own device or your notes during the exam. This is what I feel I should suggest. Now, I open the field for questions, but before asking questions, I want to thank you, as you see on the screen, to thank you very much. I understand that attending in physical presence is it's an effort, and I thank you very much, and in particular to those who are attending in physical presence, but in general, I also thank the people who attended remotely, which because I really appreciated your presence, and I really would appreciate if you give me additional feedbacks besides what you brought in your survey. And if you have suggestions to give to me of any type for shaping better the scores for the next year, I would be really pleased to get them. Now, questions. Yeah, there is a question. You mean, say again, students with? Yes. Ah, okay, yeah. Yes, I need to know it in advance, okay? And it is, let me think about, I think I can set up individually an extended time. This is perfect. On the other end, I need to know it in advance. Okay, okay, perfect. And the question was for students with DSA, is an additional time allowed? Yes, I think there are also rules suggesting 10% or more. I don't know. I am complying with what the university suggests. No problem at all. Other questions? Good. Thank you very much, and hope to see you at the exam, of course. And let's keep in touch in any case. Okay, good, thanks.
Grazie, speriamo allora di vederci il prossimo anno.
Sì, io penso di sì, perché il Dipartimento ha consentito, cioè sembra che stia consentendo ad attivare il corso a proprie spese.
Molto
Quindi-
bene.
Bene.